So a nice thing about these properties over here that we're looking at on the right hand side of our screen is that we can use them to help us simplify all kinds of expressions in order to evaluate them, sometimes without a calculator. I'll give you an example right here. Let's discuss this problem right here. We've got the logarithm base 3 of the fourth root of 127th. Well, first of all, a little algebraic simplification might be helpful right here. I'll point out that this is really going to be the same thing as taking a logarithm with a base 3 of 127th to the 1/4 power, right? 1/27th to the 1/4 power. And so by our exponent rule down here, our power rule, we can rewrite that as 1/4 times the logarithm base 3. But I'll notice one more thing. In this logarithm, 1/27th is the same thing as 3 raised to the negative third power. Well, that's interesting because we have a logarithm base 3 of 3 to the negative third power. That negative 3 can come in front, and we're left with negative 3/4 times the logarithm base 3 of 3. And we know that by our basic properties, this last thing becomes 1. And so this resulting expression would be negative 3/4. Right, well, that's actually pretty useful as a result. There's actually a few other results that we can use right here. I'm gonna shuffle around some problems over here on the board so I can fit everything in. So let's move this down right here. I'm going to take my logarithm expressions right here that we're going to rewrite in a minute because we kind of see how this is going to work out already. Let's talk about this natural logarithm of 3 times e to the 4th. Well, let's rewrite it. If we rewrite it properly, this is really going to be the same thing as by our product rule. It's 3 times e to the 4th right here. We want to break that up. So that's going to be the natural log of 3 plus the natural log of e to the 4th. Well, natural log of e to the 4th is the same thing as taking the natural log of 3, let's see, that's our first term, plus 4 times the natural log of e. And we know that the natural log of e is like saying the logarithm base e of e. So if we think about it that way, and that's the way it thinks about itself, see, our resulting expression will be the natural log of 3 plus 1 more. All right, here's some more problems, right? Let's try this. Let's say we were asked to rewrite the following expressions as a sum or difference of logarithms. Well, first things first, right here we've got this logarithm base 6 of 1 over z to the 6th. It's a fraction. That's our quotient property, right? My advice is when you're using these rules, try using each rule one at a time until you're really used to it. So right here, we've got a logarithm base 6 of 1 minus the logarithm base 6 of z to the 6th. So what could we do with that? Well, in this case, this is one of our basic properties again, right? This quantity, logarithm of 1, doesn't matter what the base is going to become 0. And we're subtracting from that logarithm base 6 of z to the 6th power. Well, that exponent can come in front by our exponent rule right here. So we're going to get 6 times the logarithm base 6 of z. Well, we don't need to carry this 0 around with us. We can just simplify that one more time and say, well, look, this is really just negative 6 times the logarithm base 6 of the variable z. That's a lot simpler to deal with. All right, now let's try another one down here. How about this guy right here? We've got the logarithm base 4, the logarithm, let's just, it looks like a common logarithm, right? There's no base, right? The logarithm, the common logarithm of 4 times x squared plus y. So we actually got a product of 3 things this time. Well, that's a good thing for us because actually these logarithms, they do expand. So our product rule right here, the logarithm of u times v equals the logarithm of u plus the logarithm of v, can be expanded to handle 3 items in our product rule, right? And we'll stop right here for a moment. And as we were stating, right here, this logarithm can be expanded out as a logarithm by our product rule up here. Let me get my pen going. Come on, pen. Equals the same thing as the common logarithm of 4 plus the common logarithm of x squared, because it's 4 times x squared, plus the logarithm, the common logarithm of y. And actually, there's one more thing we can do, because again, by our power rule right here, we have x squared in the expression, and so we can rewrite this as our logarithm base 10 of 4, it's a common logarithm of 4, plus, let's take that exponent down and make it 2 times the logarithm of x plus the logarithm of y, and that is our simplified expression. Okay, one more here. Let's try this natural log thing. Well, we notice that we've got this radical out here, and this is where we need a little bit of skill in rewriting logarithms in terms of, or exponents, radicals, that kind of thing, in terms of exponents. So let's rewrite it once. This is, in fact, the same thing as taking the natural logarithm of the fraction quantity x plus 1 divided by z, all to the 1/2 power. All right, so what could we do with that? Well, in this case, we could take that exponent down in front and say 1/2 times the natural logarithm of the quantity x plus 1 divided by z. And if we're using our quotient rule now, this 1/2 is going to be multiplied by the difference of the logarithm of the numerator minus the logarithm of the denominator. So let's take one more step here. We're going to have 1/2 times the natural logarithm of the quantity x plus 1, which is from the numerator, minus the natural logarithm of z. And then we stop. We cannot split this up anymore. This cannot be simplified because we have no rule that tells us the logarithm of a sum or difference is equal to, well, anything other than itself. So this cannot be simplified further. And so we're done. This is, in fact, the simplified expression unless we distribute the 1/2 to both terms in the quantity and write it as 1/2 times the natural logarithm of the quantity x plus 1 minus 1/2 times the natural logarithm of the quantity z. And we would be done.